experts believe that we're going to be able to solve these problems and have a completely functioning, stable quantum computer within the next 5 to 10 years, with IBM saying 5 years. Now, you might be saying, I thought we had quantum computers now. Doesn't IBM, Google, and several others have them? Can't I even sign up to access them via the cloud? Well, as we'll see later, we do have quantum computers, but they're not able to maintain their state for very long. So they're mostly useful for research and very small applications, not for full-fledged computing yet. Well, how did all this start? In 1982, Richard Feynman came up with the idea. Now, he didn't actually do any work in quantum computing. He simply speculated and posited that why can't we store data and process data in quantum states, in qubits instead of regular bits? It just so happens that Richard Feynman was such a preeminent physicist, not just a Nobel Prize winner, but just so well known in physics that his mere speculation got other people thinking and following that trail of thought. Now, when we talk about quantum computing, depending on how deep you want to get into it, at some point, you're going to have to get at least the fundamentals of quantum physics. Not today, not for our current presentation, but at some point. And usually mathematically, that means a working knowledge of linear algebra, complex numbers, and at least basic differential equations, ordinary differential equations. Now, that at least gets you running. Here's the problem you will encounter. If you have all that background, there are things in quantum physics that we can prove experimentally are exactly how things work, but no one knows why. There are things we just don't know why. And Richard Feynman had said, and this is a quote, "I think I can safely say that nobody understands quantum mechanics." There are lots of things we can talk about. Quantum entanglement is one we'll talk about in a little while, that we know it occurs. We don't know why. Now, looking through a bit of a timeline, in 1985, David Deutsch developed the quantum Turing machine. It was a conceptual machine, not a real quantum computer. The big news for us is Peter Shor came up with an algorithm to factor very large integers into their prime factors. Why does that matter? Well, as we'll see later, the security of RSA is completely dependent on the fact that it's difficult to factor a large integer into its prime factors. So difficult that it's not really practical to do it. And a lot of e-commerce today is using RSA encryption. So if we have a working quantum computer that can factor large integers into their prime factors, then RSA would no longer be secure. In 97, Grover's algorithm was able to do searches in a much more efficient way. Now back to Peter Shor. Here's the issue. You can certainly factor any number into its prime factors, but it's really a lot of trial and error. It's so difficult that it could take longer than is practically possible. Well, his algorithm was able to factor a large integer into its prime factors in what mathematicians call polynomial time, basically a time that can be expressed as a polynomial. And in this case, it's actually log n, with n being the integer. So whatever size integer you have, in log of n, he can factor it. And that does not mean that if I had a fully functioning quantum computer today, that I could push a button and derive your RSA private key from the public key. It does mean that I can take your public key and probably within a space of a few weeks, if I had a fully functioning quantum computer, get back your private key. And as we'll see later, that's a major problem. Peter Shor's been lauded for a lot of his work. He is one of the rock stars in quantum computing. I like to refer to him as the Mick Jagger of quantum computing. Now, I'm not going to make you learn this equation, but Schrodinger's equation is so fundamental to quantum computing and quantum physics. There are two things you need to know about this. First of all, to really get serious about quantum computing and quantum physics, you need to have sufficient math that you can at least generally understand this equation. But more importantly, if you don't want to go that far, you just want the highlights, One of the bizarre things about quantum computing is it's largely probabilistic. That's because quantum physics is probabilistic. Basically, we can say with a high probability, at least in some cases, that a given thing will occur, but we cannot say with certainty. And that leads to quantum computing. So one of the problems that doesn't get as much general press, but it's a hot topic in the quantum computing world, is error correction, because you get a lot more errors in quantum computing because of the probabilistic nature. So being able to account for that and accommodate for it is really critical. There are really two branches, quantum key distribution and quantum computing. They're both under the umbrella of quantum computing, but they're a little different. Now, quantum key distribution, there are many protocols, but I've put a few here that allow one to exchange a secure key over an insecure medium using quantum states. Now, some of them are based on the fact that when you measure something in the quantum world, you change it. So if I were to send you my key that I wanted us to use, but I send it to you in quantum states, if someone else intercepts it and tries to read it, well, the reading will alter it and the recipient will detect it. That's the most common general approach to quantum key distribution. But there's another one. And here's one of those just weird things about quantum computing that if I could explain to you why this was true, I would be in Stockholm collecting a Nobel Prize. And I'm not. So I don't know why this is true, and no one else does either. If I take two subatomic particles, let's say 2 photons, and I slam them into each other at a high rate of speed, I generate 2 new particles that are quantumly entangled. What does that mean? Well, I could say this in a very mathematical way to indicate that their quantum states are strongly correlated, but a more general way to put that is their states are intertwined. So let's say my 2 entangled particles are photons, and they have a property called polarization. If I alter the polarization of one photon, the other one will instantaneously alter in response. Now, by instantaneously, they have shown that even if these 2 entangled particles are separated by thousands of miles or kilometers, it still happens instantaneously. Now, as you might imagine, during Einstein's life, he had a problem with that because relativity teaches us that nothing can accelerate beyond the speed of light. So nothing can be instantaneous. But as far as we know, this is instantaneous. And many, many experiments have proven that. Now, there are a ton of hypotheses as to why that might be the case. So far, none have shown to be valid. We just don't know. But it really makes a great way to exchange a key, because if I represent bits as quantum states, and I change a bunch of bits here, and they automatically change for the recipient, well, since I'm doing this via quantum entanglement, and nobody knows how quantum entanglement works, nobody could have intercepted it. Now, that is one way, but the more common way is to simply use quantum states such that the state will be changed if someone tries to measure it. So that's a little easier and that's a little more common. There are a few companies that are actively doing quantum key distribution now, at least on a research level. So this is something that's very far along, much farther along than quantum computing. Now, as we discuss the problems with quantum computing, the timeline will help. And I won't read every element on this timeline to you. I just want you to get some highlights. The first 2-qubit machine was built at UC Berkeley in 1998. So 22 years ago, we had our first 2-qubit machine. The first 5-photon entanglement in 2004. 2006, the first 12-qubit quantum computer. Yale University created a quantum processor. By 2011, D-Wave has built their own quantum computer. Now, they use a slightly different process. They're not using typical quantum gates. They're using what's called quantum annealing, which is a little more complicated, and it's really thought of as pseudo-quantum computing. So they will generate a lot of more bits, but they're not normal qubits. So it seems like they're further along than they are. This next thing I want to point out to you is probably the most critical for understanding why we don't have working quantum computers now. Decoherence was suppressed for 2 seconds at room temperature in 2012. What is decoherence? Well, the problem is quantum states don't stay the way they're supposed to be. They decohere. They essentially fall apart in a very short period of time. Most of the approaches to combating that have been supercooling the quantum computer. And by supercooling, I literally mean anywhere from 3 to 5 degrees Kelvin, which, if you don't remember your chemistry and physics, is a little more than 270 degrees below zero. So you're unlikely to have a quantum computer in your home office anytime soon. I don't think you could foot the electric bill for that kind of cooling. That's been a problem. Getting quantum computers that can keep from decohering for a long time, for hours and hours, at a temperature that doesn't require such supercooling will be required before we're able to fully implement quantum computing. Moving along, we have 2017, IBM unveils a 17-qubit computer. Later, a 50-qubit computer. Google announced a quantum chip in 2018. Same year, Intel gives us 49-qubit superconducting chip. 2019, IBM 53-qubit computer, and just this week, they've got a 61-qubit computer out. I just was reading that earlier this week. This year, quantum engineers report they've created artificial atoms and silicon quantum dots for quantum computing. And in March of this year, they found a way to correct signal loss in quantum networking. Now again, why do I say RSA is not dead today? Well, I just proudly announced to you IBM announcing their 61-qubit computer. But here's what we really need, and we need these stable and not decohering. We need about 4,000 qubits to effectively factor 2048-bit RSA. So we're not even close to that yet. The reason this is a concern for cybersecurity is most people agree we will get there, and it may not happen in this gradual progression that we've seen. You may have a sudden leap forward, forgive the pun, but a quantum leap forward when we suddenly accelerate a lot. If that occurs, RSA will quickly become unusable. Some exciting trends going on. These links here are important because, for example, the first two, you can actually sign up and for free access limitedly these quantum computers. There are people developing quantum computing programming languages. IBM QuizKit, Microsoft's Q#, quite a few of them. There are online simulators you can use. And there are various standards being put in place right now to standardize quantum computing. IBM have announced a 58-qubit quantum computer that they're selling commercially, and University of Chicago has put together an exchange for all researchers working in quantum computing. But that most prominent obstacle is controlling decoherence. Normally that's done by isolating a system. We isolate it so that, sorry, didn't mean to go forward. I was trying to read the chat room there. We isolate it so that we can keep it from being affected by the outside environment, because if it is affected, then it will decohere right away. So what is the magic on qubits? Why do we care? A classical bit is a 0 or 1. And when you measure it, you will get a 0 or 1. The issue with the qubit, and if you'll notice that's a small animation in the left-hand corner, it moves every moment or two. A qubit is storing some value in a quantum property, let's say polarization of a photon. Now, when I measure it, I will get a 0 or 1. But before I measure it, it could contain any superposition of those states. It's often represented like this in what's called a Bloch sphere, because until I measure it, it could contain any value on the sphere. Now, it will ultimately be measured, and that superposition will collapse into either a 0 or 1, but until that measurement, I've got virtually infinite values in there. Sometimes we use this as light pulse frequencies or energy states of an electron. The electron's at a ground or excited state. Any of these can be used to store a qubit. And we might have a 3-qubit register where we look at the values of each qubit, and together they provide the value of the register. But the more qubits I put in there, the more decoherence becomes a problem. So growing the quantum computer is a real challenge. How do we store them? Well, ions have been used for a long time simply because they already have a charge, so it's fairly easy to store data there. Neutral atoms are just now being used by a few researchers just in the past 3 years. And that's listed in this paper right here from Physics Today in 2017. They're just now getting to the point that they can trap neutral atoms, usually using magnetic fields, but some other techniques have been used. And these are exciting because they're more stable. What is a quantum gate? Well, let's pause and discuss what a logical gate is, period. Excuse me. In your computer that's sitting in front of you right now, everything, as you know, ultimately comes down to ones or zeros, which means everything has to be processed by manipulating ones or zeros. And the way that's done is by passing those ones or zeros through what are called logic gates. And what the logic gates do on your computer is they do a binary logical operation, like a binary AND or a binary OR. And in fact, it turns out that the not AND gate is a pretty good one for doing normal operations. Well, in quantum computers, we need quantum gates. We need to make sure that we can put in qubit values and get out some value from an operation. Now, if you think about that for a moment, it's not that different than your classical computer. And as I just said, you may not think about it often, but it doesn't matter if you're doing the most complex partial differential equation mathematics you can imagine. On your computer, it ultimately comes down to ones and zeros going through logical gates, doing an AND, a not AND, an OR, a not OR, that kind of thing. We have to do the same thing in quantum computers. And that doesn't get most of the popular attention, but it is very exciting research in the actual quantum computing world as we try to develop effective universal quantum gates. It turns out that a thing called a Hadamard gate is probably one of the best, simplest to use quantum gates. It's also known as square root of not gate. And if we put enough Hadamard gates in succession, we can pretty much do any mathematical operation we want. Quantum annealing I mentioned earlier, basically you start from some superposition of all the candidate states with equal weights, and think of weights kind of like a neural network, and it evolves via some time-dependent equation to the right answer. The name actually comes from metallurgy. Blacksmiths would heat a metal till it glows, then let it slowly cool to room temperature to increase strength and hardness. Quantum annealing is a similar thing with quantum data, and that's how D-Wave does their computing. So D-Wave might tell you they have a 1,000-qubit computer, but they're not using quantum gates. They don't have the decoherence issues. It's not a true quantum computer, although it's very effective, very useful. In fact, even NASA is using one of the D-Wave computers, so it is definitely a laudable project that does quite well. It just doesn't give us everything we're looking for in quantum computing. Now, IBM and D-Wave both have made their computers available. With D-Wave, you can sign up for free. With IBM, they have both a free and a paid for version, so you can do real quantum computing experiments today. Now, quantum computers don't do everything well. I've heard people say quantum computers will change everything. Well, think about supercomputers today. Most people would not benefit from a supercomputer. If you're surfing Google, writing a Word document, checking your email, and playing Fortnite, a supercomputer is not going to change your computer's behavior at all. However, if you're doing intensive data science machine learning, heavy-duty mathematical calculations, then a supercomputer would be great for you. Well, a similar thing is going to be true If tomorrow they solve the decoherence problem and there's a 50,000 qubit quantum computer available, it would be great for things like solving integer factorization, solving the discrete logarithm problem, doing database searches, solving linear systems of equations, but it wouldn't affect many other things at all. That's why I say it's not going to affect everything, it will affect some things. So what is the problem for cybersecurity? It's those first two things I just mentioned. RSA is predicated on the fact that it's really hard to factor a large integer into its prime factors. Diffie-Hellman and all the variations like MQV and El-Gamal are based on the fact that it's really hard to solve the discrete logarithm problem. In fact, even elliptic curve cryptography is a discrete logarithm with respect to a point and an elliptic curve. So if we have a fully functioning working quantum computer that has solved the decoherence problem, those problems are no longer hard to solve, and therefore all of those algorithms are no longer secure. Now, what does this mean? First of all, the first way quantum computers are going to be implemented is just the same way traditional computers were. At first, they're accessible to organizations with large budgets, major universities, government agencies, that sort of thing. Well, that's a problem. If an adversarial government agency solves the decoherence problem and doesn't tell anyone but keeps it secret, then they can begin cracking all that e-commerce communication, online banking, secured email, all of that stuff, and reading and intercepting whatever they like, whenever they like. So this is actually a national security issue. Secondly, if a hacker could get hold of this, normally a digital certificate is issued for about a year. If it takes me 2 weeks with a quantum computer to crack your RSA or elliptic curve key, okay, I've got 50 weeks left of being able to read your transmissions as if they were published on a billboard. So if, for example, I crack Amazon's keys, then all those purchases made on Amazon, I can intercept them, get the credit card numbers, do whatever I like. This is a very serious problem. It's no longer just theoretical stuff for engineers and physicists to play with. Fortunately, the National Institute of Standards has been working on this problem for a while. They did the same thing with AES back in the late 90s to 2000. They invited anyone to submit an algorithm that they believed would be quantum resistant. Submission deadline was November 30th, 2017, so it's too late to get in on it. But they had first one round of analysis and study that eliminated a lot of candidate algorithms. Then they had a second round. And now they're moving on to the third round. And in that third round, they are appealing to cryptographers around the world to do their own analysis on any of the third round candidates. And I just published a paper about a month ago with a team of 4 or 5 other researchers at different universities, where we took another very broad-based look at NTRU and once again established that it's pretty secure. Now, the reason for NIST doing this and encouraging all these other people to do it is before they pick something and say, this is the standard for quantum resistant cryptography, they want as many eyes as possible to be looking on it. If there's a flaw, let's know it now and either eliminate that candidate algorithm or fix the flaw. Let's not wait until we've adopted a standard and a year later find out it's not as good as we thought. The point of all this being, whereas quantum computing has terrible ramifications for cybersecurity, it is being worked on now. It's been worked on for quite a few years. And some of these algorithms are actually 10, 15 years old. It's just until quantum computing advanced to where it was now, these algorithms weren't considered for practical use. They were just intellectual exercises. But when quantum computing advanced, people suddenly started taking a harder look at these algorithms. So we have years of cryptanalysis to start with. We're not starting from scratch. These are the 5 major approaches people have done. Lattice-based algorithms, which we're going to talk about a lot, primarily because several of those algorithms have made it to the NIST third round. Multivariate cryptography, supersingular elliptic curve isogeny cryptography, hash-based and code-based algorithms. We're going to focus on the lattice-based because, as I said, many of them have made it to round 3, and it's a little easier to wrap your head around. Now, don't panic. You don't have to know all the math here. If you have a good, strong working knowledge in linear algebra, this will be okay for you. Basically, lattice-based cryptography is building algorithms based on problems in lattices. Now let's pause for a moment because you may or may not have a strong background in crypto. I keep mentioning mathematical problems. Well, even aside from quantum computing and quantum resistant algorithms, we have symmetric and we have asymmetric algorithms. Symmetric algorithms scramble the message up so that if you don't have the secret key, you can't unscramble it. And frankly, there's millions of ways to do that, and there are hundreds of symmetric algorithms. Well, asymmetric cryptography is created such that I have one key that will encrypt and a different key to decrypt. That allows me to distribute that encrypting key to anyone who wants it. And all you can do with it is encrypt a message to me. You can't decrypt a message sent to me. It allows us to avoid the problem of key exchange. Without asymmetric cryptography, there'd be no online banking, e-commerce, online education. Now, it turns out that there aren't that many different ways to do asymmetric cryptography. We have to have that private and public key mathematically related, and they're related based on some mathematical property. So there has to be some underlying number theory. And we want to find a relationship that's easy to solve if you know the keys, but practically unsolvable if you don't. So we're looking for things that are mathematical problems that are difficult to solve. Lattice-based cryptography looks at problems related to lattices. Now, before we go any further, let me elaborate on lattices for a moment. If you've ever taken a linear algebra course, most of the matrices that are presented to you are rather small, two-dimensional, maybe 4 by 4, 5 by 5 at most. That's because that's what you can put on the page of a textbook. But nothing prevents you from having a lattice that's 5 billion by 5 billion, or maybe even more dimensions, 5 billion by 5 billion by 5 billion by 5 billion. That's just a little tough to print on a textbook page. So when you're thinking about lattices and problems, keep in mind how big and complex a matrix may be. Because if you think about that little 4 by 4 matrix, you think this isn't a tough problem. I can look at the matrix and solve it by eyesight. With that said, let's go forward. Lattice-based cryptography looks for problems in lattices. One is the shortest vector problem. So I've got a lattice, and remember, you can think about 4 by 4 lattices, but they can be a lot more complex and large than that. How do I find the shortest vector within the lattice? Well, that's really, really hard to do in a really large lattice. And because we have a problem that's hard to solve, we can use that as the basis for an asymmetric cryptographic algorithm. Learning with errors. Now I have a confession to make. When I originally did a study on several algorithms, I wanted this one to be the most secure, but it didn't turn out to be. The study did not show it to be, and many other studies have also not shown it to be. The reason I wanted it to be the most secure is I'm a huge fan of interdisciplinary approaches, and this is actually a machine learning program. And they combined machine learning with cryptography, and I love that idea, but it turned out there are some serious flaws with the implementations. GGH has been around for a long time, named after its inventors, first published in 1997, and it's looking at the closest vector problem. So I have some vector space, and I have a lattice, and I have a vector that may or may not be in that lattice. So I want to find the vector inside the lattice that's closest to the vector V I picked. Again, if we're talking about a 4 by 4 or 5 by 5 lattice in a vector space that may be a little larger than that, you could look at it and figure that out. When we talk about unknown number of dimensions and sizes, that becomes really hard to solve. Now in TRU, my own studies have shown this to be one of the more secure, and NIST has taken it to round 3. In fact, 2 versions of NTRU made it to round 3. In addition to being very secure, it has actually already been shown to be resistant to Shor's algorithm. That's kind of important, since Shor's algorithm is what got all this ball rolling. When we saw that, hey, RSA is going to be insecure due to Shor's algorithm, we started looking for alternatives. So it's kind of important to ensure that that alternative is resistant to Shor's algorithm. Now, let me make another point just for your edification here. Let's assume some of the naysayers are right and we don't fix the decoherence problem in the foreseeable future. And 10 years from now, we still don't have a quantum computer. All of this talk of quantum resistant cryptography was not wasted, and I'll explain why. RSA was first publicly described in 1977 by Ron Rivest, Eddie Shamir, and Leonard Edelman, and it was incredibly innovative. But 1977 was a long time ago. 43 years ago, I suspect there are people in this conference that weren't born yet. And time has moved on. And even with classical computers, you might have noticed if you purchase digital certificates, the certificate authorities keep requiring larger and larger key sizes. Nowadays, about the minimum you can get is 2048 bit. Just a few years ago, it was 1024. What changed? Well, people using classical computers in either a cluster or a cloud formation have been able to crack smaller keys. The first such study I read was 2008. Some researchers at a university used 80 processors and in a period of 6 months were able to crack 768-bit RSA. Well, you may think no one uses 768-bit RSA anymore. That's because it's been cracked. You may think, who has 80 processors? Anyone with access to a botnet or cloud or cluster, certainly nation states. You may think it took them 6 months to crack it. Well, as we already said, digital certificates are normally issued for a year. So if it takes me 6 months to crack yours, I have 6 months remaining to abuse your secure communications at will. This chart just basically gives you an overview of some of the major lattice-based algorithms, what problems they're based on, and a little brief description. Now, GGH still has solid mathematics, but many of the implementations have been successfully attacked, so I suggest variations be explored. NTRU appears to be sailing forward, and learning with errors key exchange protocols have been found to be susceptible to a number of attacks. Now, we don't have a lot of time left, but I'd like to end on something a little more thought-provoking. Everything up to this point is very rooted in solid engineering. We're not getting speculative at all. We're going to lean towards the speculative in a moment. What about quantum computing and machine learning or AI? Well, to begin with, there's two approaches here. Can we use machine learning to help us develop quantum computing? In other words, could machine learning algorithms help us solve decoherence? A lot of work being done there. The other side of that is, will quantum computing provide better machine learning? Once we fix decoherence, will neural networks, for example, or k-means clustering, or whatever algorithm you like, will they work better on a quantum computer? Possibly. Grover's algorithm is an algorithm that's used for searches where they're already implementing that into machine learning and combining them to improve machine learning processes. So we're already combining things from the quantum world with machine learning. All kinds of stuff going on. We have classical machine learning being applied to data from quantum experiments. We have quantum enhanced machine learning. So we use quantum algorithms to solve our machine learning processes. Quantum analogs of neural networks, hidden quantum Markov models, all kinds of things happening. This is a very exciting area of research, and it will impact cybersecurity as well, because another hot topic in cybersecurity is integrating machine learning with cybersecurity, both defensively and offensively. Lots of quantum algorithms for machine learning are already being implemented, and we're trying to improve classical machine learning with offloading some of it to quantum. Quantum neural networks are already being worked on to give the quantum equivalent of a perceptron If you've ever taken a machine learning class, you've worked with a perceptron. Here are just a few noteworthy projects. I am aware that time is slipping away from us. Here are some projects going on right now with quantum AI. And this is just a quote from an individual working on a complete dedicated neural network computer using quantum technology. 2019 DesignCon, Quantum Nanoscience Laboratory proposed artificial intelligence to solve grading quantum computers. Harvard published work on quantum circuit-based algorithms inspired by convolutional neural networks. And it goes on. I won't read all of these to you. If you don't have access to the slides, you can always email me and I'll send them to you. So now I'm going to have to stop the slide so that I can see the chat window. When I tried to look at it before, something happened and I couldn't see the chat. And I'm still not quite seeing the chat, but I'd like to open the floor for questions if I can hopefully pull up the chat window.
If you can't get it to work, just let us know and we can always read the questions to you.
Well, hopefully I'll be able to actually make this work. But if you see a question now, please feel free to read it to me.
There is one. He asked, why is SVP a hard problem? It would seem that you would calculate the distance of each vector in the lattice and find the shortest distance.
Well, that's actually a good question. But when we're talking about a huge lattice, each vector could be trillions of vectors. So calculating the length of each vector and trying to find the shortest vector suddenly became a lot harder problem. It became the proverbial finding a needle in a haystack. Oh, now I'm seeing a chat window. Any other questions? This is odd. Normally I'm inundated with questions at this point. Well, I am going to put my email in the chat window. So if you would like the slides or you come up with a question later, feel free to email me.
And as mentioned, the recording of this talk as well as the slides will be available on the community. So of course you're welcome to email Chuck, but you can also look there in the next few days and that will be available.
Okay. Well, it appears there are no questions. I'm going to stop sharing my screen.
Okay, well, Chuck, you're more than welcome to stick around. Otherwise, we are going to take a short break while we prepare for the 2 o'clock presenter. So if everyone could be back here by 2 p.m. Eastern Standard Time, we would appreciate that. Thanks very much. And Chuck.